So welcome to this webinar, which is organized by the TC20 of the International Commission on Glass. And it is co-organized with Laetitia Petit, who is here, and it is organized in the context of the International Year of Glass, which will end in a few weeks now already. So today we have the great pleasure to have Kathleen Richardson, who is a very top-ranked glass scientist in the world. So it's a very great honor, and thank you very much, Kathleen, for accepting this invitation to give this webinar. So Kathleen is a professor at Creole, University of Central Florida, and among all her activities, I just want to mention that she is highly involved in the organization of this International Year of Glass, in particular in the US. So Kathleen, we are honored to hear you and learn more about this infrared glasses and the future of the photonics with this glass.
Well, thank you, Wilfred, and thank you, Letitia. I'm so excited to be here and to speak to you about infrared glass, which may be a topic that you know a little about, but hopefully I'll go into a little bit more detail. I want to thank Wilfred and Letitia for leading a lot of the activities for the International Year of Glass for TC20. They've done a great job of organizing this series of webinars, as well as we have just submitted a very large research review paper on various aspects of glass. So if you're interested, you can look forward to that coming out. And certainly when it does come out, I'm sure we will highlight that on the TC20 website. So I am going, first of all, let me apologize because I'm going to talk fairly quickly through many topics, but as you'll see, I'm going to post my slides, and I'm also, since we're recording, if you would like to review these after, and come back to me with some questions, please feel free. My email is shown on this cover slide, and I would be happy to hear from you. Just remind me that you listen to my talk, and then we can certainly go into more detail. So I gave a talk at the opening ceremony of the International Year of Glass, which was held in February in Switzerland. And I really made that a very straightforward, simple, educational talk for the diverse group of technical and non-technical people that were attending that. And this talk has been extended just a little bit to put a little bit more science and engineering. Now, I don't expect you to be experts by the end of this talk, but hopefully I will be able to give you some key points in terms of what infrared glasses are, why we care about being able to engineer their properties, how it's not just changing the chemistry, but also changing how we make them and how they can be adapted onto platforms. And that's what I really want to talk about today. So the title of my talk is Seeing and Sensing the Future Enabled by Infrared Glass Innovation. And goodness, here we go again. Let's see. All right, there we go. First of all, I want to acknowledge this work that I'm going to share today was funded by a variety of different organizations and collaborations that supported this, namely a number of students and postdocs and staff from both my team and my collaborators' teams have participated. So I want to say a special thank you to them because their work is integrated into this presentation. You will have this to look at if you so choose, but this just gives you a snapshot of where my group is located physically at the University of Central Florida and what some of our experiences are both in research areas for various applications and some of the facilities that are very unique to our group and our efforts on making broadband glass and glass ceramics. And I'll talk about what that means in just a moment. So to take a high-level view and then dive deep, my group, which comprises the Glass Processing and Characterization Lab at UCF, really focuses on future optical systems. And the boxes with red text show kind of the key things that we think about every day in terms of being able to design new materials. But we work on the items in the black text boxes specifically because all of the applications that people come to us interested in engineering better materials for typically have some list of properties that they must have. And so we need to think beyond just the glass chemistry, but how we're going to make it, how we could potentially scale it up, because I think you appreciate if you want to make new materials, at least our goal is to make sure that we've thought about how you scale them up, how you make them in big sizes. And as you'll see, when we talk about big sizes in infrared, it's different from big sizes in oxide glasses, which are probably the glasses you are most familiar with. So scale up becomes important. And also being able to understand how the glass might be used, because as you'll see in one of my slides, which has the title, Chalcogenide Glasses Don't Live Alone, because they're usually integrated into some kind of an optical system or an optical package where they have to coexist with other semiconductor materials, other crystalline materials, and thereby they have to not change their properties that we've engineered them for once they're used. So these are all the things that we think about when, and are available to us in our toolbox when we think about engineering a new material. So I think most of you can appreciate the various things, whether it's beauty, strength, architectural robustness, or unique form factor. When we typically think of glass, we think of oxide glasses. And those oxide glasses can have specialized properties, but they do not transmit much past about 3 or 4 microns in the infrared. And I'm going to talk about that spectral window and what that means. If we think about infrared glass, there are things that we can do very similar to what we do with oxide glasses, but what's special about them is they transmit in the infrared. And that means most of them, depending on their composition, don't transmit in the visible. In the upper left-hand corner, you'll see some arsenic sulfide glasses or sulfide glasses that do have some transmission in the visible. But to large part, unless they're doped very specifically, which typically means in chalcogenide glass speak, without selenium, these glasses typically are black or silvery in color, such as shown in the middle. One of the things that's interesting to understand is if we have a material that starts out glassy, we can convert it either to a glass ceramic. Depending on its composition, we can make the pattern structure that you see here in the middle where my cursor is. This is a lithographically produced thin film of optical phase change material that's based on many of the ingredients that we use to make glasses. But we deposit this material as a film, as I'll talk about at the end of my talk, and it has some very unique properties in that it can be switched, activated by either laser light or current to change from its amorphous state to a crystalline state and then back again. And that is where the word phase change comes from. So I'll talk a little bit about this. The form factor is important, whether we're talking about thin films, bulk optics, or fibers. Chalcogenides are nice in that they can typically be formed into glasses at low temperature, so much lower temperature than that used to make oxide glasses. So I'll talk about that in a moment. For those of you who aren't familiar with what chalcogenides are, I'll use the shorthand CHGS as chalcogenide glasses. They're typically based on group 6 elements, so those shown in the red box, sulfur, selenium, and tellurium, and they're typically bonded to other constituents, most regularly in the group 4 or group 5 columns of the periodic table. And as I mentioned, they can be formed and are widely used as lenses, fibers, some applications where they've been made into microspheres, and then in optical phase change applications such as the meta switches shown. And I'll talk about what these things are. So if we think about making these for a variety of applications, we need to understand what the flexibility of these materials are. And so I'm going to call these knobs. Think of knobs that you can tune or change to allow us to really modify to our desired outcome the application that we're looking for, the materials to support that application, whether it's seeing and sensing or some other application. So the key things we need to think about are shown here in the red box. We can certainly change the chemistry and thereby the structure of the glass, and this will allow us to change not only the optical properties, but many of the other properties. The bonding in chalcogenides is typically mixed between covalent and van der Waals forces, which in this arsenic sulfide layer structure, covalent bonds exist within these layers, but it's van der Waals forces that bond these weak bonds in between layers. So because these are big anions and cations that participate in these structures, their bonds are typically much weaker than that found for metal oxygen bonds in oxide glasses. So as a result, these materials typically have much lower TGs and much steeper viscosity temperature curves. The other thing that we can use as a knob with these, and the low temperature aspects of these glasses allow us to very easily switch from bulk materials to thin film materials to fibers, because they are very amenable to shaping in a variety of form, what I call form factors. And then the other thing that many people who don't know think of as a limitation, these materials can be made tunable. And what do I mean by tunable? It means that we can engineer into the composition attributes which make them amenable to modification, whether that means deposition into thin films, whether it makes them amenable to optical phase change, which I alluded to, which is the ability to change from its amorphous state to its crystalline state and then back again by use of some stimulus. Or it can make them laser structurable, whereby the laser that interacts with the structure of the glass can change its extent of polymerization and therefore make it somewhat soluble or very soluble to being etched. So here are some examples of some 3D written, laser written micromolds in silica made by one of our colleagues at EPFL in Switzerland, which shows that using lasers, we can either chemically or physically remove ablate material. In our application, we showed that by taking a glass, converting it to a glass ceramic, and then using laser, we could either reamorphize spatial regions or turn it back to glass, or start with a glass and then locally, using direct laser right, locally crystallize it. Suffice to say that some compositions do better than others. And if you understand this interrelationship, you can tune the material to have the properties you want for your applications. So I share with you just, there's selected references put throughout this presentation, and those references aren't meant to completely describe each of these topics, but they're typically very well referenced. So you'll find some other references to related activities that might be of interest to you. So let's talk about what we mean by infrared transmitting glasses. Well, to talk about that, the first thing we have to define for ourselves is the infrared spectral window, which is comprised of 3 discrete transmission windows in the infrared. And why we care about these windows and being able to see in these areas is primarily, and a lot of the early work was developing these materials for imaging applications, but more recently, sensing applications have allowed us to detect, if you look at these fingerprint spectral groups, they all have fundamental resonance or fundamental absorptions in these spectral windows. Now, most of the time, we can detect these species in the visible, but those are typically overtones, so the intensity of those signatures is typically weaker. If we can image weak into the infrared, we can see the fundamental resonant absorptions and thereby quantify not only who those species are, but how much of those species are present if we have materials that transmit in this window. So shown in the bottom panel is where many of the materials you might be familiar with transmit across these windows. So the light gray is where these materials are transparent. The black or dark gray is where they are opaque. And what you see is that one representative glass material, arsenic selenide, transmits very broadly over this full region. And so if we can think about making these materials, and this is just one composition based on arsenic and selenium, in a form factor that allows them to be integrated into structures that can be put into sensing applications, we can use it to detect a wide range of species. So let me just redefine these spectral windows again. Here's a slightly different image of the same information, but I want to define the three different regions. People argue about what the specific cutoffs are, and I don't want you to get sidetracked on these, but typically the SWIR shortwave infrared or the near infrared is typically in this lower wavelength, higher energy region, and it typically overlaps with a little bit of the visible. So if you remember, your red Heaney laser pointer transmits at 0.63 microns or 632 nanometers in the red. And typically it's the end of this visible region to about 2 microns or 2.5 microns that constitutes the SWIR. We typically talk about the mid wave is the mid region, the 2 to 5 micron, and the long wave is the 7.5 to 14 microns. Sometimes this is 8 to 12, 8 to 14, depending on who's trying to do what with the material. They define it slightly different ways. But suffice to say, there are 3 distinct regions of transmission that are surrounded by absorption, either due to moisture or to CO2, that we typically discuss when we talk about infrared. In a perfect world, you would have one material that could be a broadband material that would span this entire spectral region. But we know because of fundamental chemistry and physics, most materials have a fundamental absorption limitation due to the resonance of the ingredients in their structure. So this is why oxide glasses typically turn off or become opaque in the 3 to 5 micron region, depending on who the cation is, and why infrared glasses turn on in the red or SWIR region, depending on who their anions are. So we typically talk about broadband. So the things I'm going to talk about today, broadband in my world means things that transmit approximately in the 1 to 12 micron range. Because if it means it transmits across that broad spectral window, then I only need one set of optics. Many of the military applications of infrared up to this point have discrete transmission or optical design criteria associated with each of these 3 bands. So that means 3 different sets of optics, 3 different types of detectors, and it makes for a very big and heavy system. As you'll appreciate as I go through, making things smaller, lighter weight, with similar or better optical function is what we call SWAP. And that's a really important driver that over the last decade has forced us to think about SWAP in infrared material design. And so it's really pushed a lot of our broadband material optimization to make not only glasses, but glass ceramics and phase change materials that have spectral windows that span multiple of these bands. Here's an illustration of why how and where those spectral bands are important. And it turns out that depending on which of these spectral regions, the SWIR, the midwave, or the long wave, each of these spectral regions has advantages over the other in terms of their ability to see information. So here's a visible image on the top, and then here's the same boat imaged with cameras that transmit in each of these spectral ranges. And what you see is that the image is largely the same, but it turns out, depending on what the surrounding environment of use is, that some of these spectral regions of imaging is better than the other. So we'll talk about this in terms of the applications. When we're talking about sensing, I alluded to the fact earlier that we want to be in the region of where the molecules or the chemical or biological species that we care about have their fundamental resonances, and those are typically in the infrared. So one of the things we think about there is, can we make our sensors so that they see in the spectral region and thereby can sense the presence of those molecules And as I'll talk about some of the early things that we started working on over a decade ago are now transitioning into commercialization. So the key takeaway here is there's 3 primary bands in the infrared, and we want to be able to design our components to either see or sense or whatever it is we want to be able to do in the spectral range of interest. And to do that, we need to tailor our material. So most of you are familiar with night vision or thermal imaging, and this is the way in the 2000s and before these camera systems were typically constructed. So infrared imaging is not new, but typically legacy systems that were used were typically very big and very heavy. So whether it's military applications or hunting applications or thermal imaging applications, the typical image system is shown in this upper blue cartoon, which is really a lens design. And the first thing you'll say is, what are all those individual bits and pieces in this lens design? Well, this is just a representative image of an afocal telescope made up of many, many, many different lenses. So you can appreciate in those old systems, these were largely crystalline, made of germanium, and therefore they were very, very heavy. So if we could even reduce the number of those lenses by 1/3, we would dramatically reduce the complexity of the optical system and make it lighter for anyone that was carrying it, regardless of their application. So here's seeing and sensing today. Many of these applications I think you can probably relate to because so many of them are related to environmental use, but people are using infrared imaging for a wide variety of applications, whether it's search and rescue, whether it's monitoring of systems, so that in standoff applications where you don't have to climb up and look at the electrical system, but you can detect, such as shown in the bottom right corner, when there's a failure. Imaging based on infrared is extremely important, but needless to say, it has to be operational in a defined spectral range of use, but it's also got to be compact, lightweight, and hopefully low cost. Here's another application that we're seeing much more of, and that is the use of infrared imaging now on a platform such as a drone, which can be flown. Many times you not only want a camera that can see. For example, here's an application of a drone being used with an infrared camera to assess disaster-related damage in terms of structural, mechanical damage, but it also can use its infrared imaging to look at defects that perhaps can't be seen, whereby either heat or cool can leak out of a building if it's damaged. So the key challenge that this illustrates is anything that we want to be able to fly, whether it's on a drone or a satellite, we need to be able to do it with a compact package size. And this is where we talk about reducing the swap and its cost. So here's our application of where, if we can make these sensors very complex, but yet very small in footprint, we have a large variety of application spaces. And I think most of these you're very familiar with. Of course, we typically hear about military applications first, because many times it's the military who pays for the initial development of these materials. But over the last decade, we've seen profound dissemination of this technology to a wide variety of applications. And what I want to take you through is how we've thought about engineering materials for these applications based on infrared glasses. So in 2011, myself, along with my colleagues at University of Sydney at the Kudos Infrared Research Center, wrote a review paper on how we can think about packaging infrared materials based on chalcogenides into photonic packages, which could be used as a way of coupling light, perhaps microfluidics and microelectronics into a compact package. And this is a cartoon of what we envisioned such a package might look like at the time. Our goal was to say, could we build a package for a sensor that could mimic in a very small scale the capabilities that we typically see in a very large footprint application, such as an FTIR. So shown on the left are meant to illustrate the contrast in size between a benchtop FTIR, which most of you probably have in your labs, and a chip scale sensor. So assume this chip is nominally about a centimeter by a centimeter square. And again, if it's on a chip, I mean on a silicon chip, and I mean that it can be processed using chip scale manufacturing practices. That makes it lower cost if I can integrate this optical function onto that. So if I could make a chip scale sensor out of infrared glass that has transmission across this 2 to 14 spectral range, I could now make a sensor that should be able to detect many of these chemical species shown in the plot above. Now, the key information in sensing that you typically want to be able to do is to define who you're looking at. So who are the species that give rise to the absorption or fluorescence that you're monitoring with your sensor? But also, that's what we typically call specificity, but we also want to know the sensitivity. How much is there? How much is there if it's something that is not so damaging or not so hazardous, such as those constituents shown in the upper plot, but if it's a toxin or some impurity or some material that in very small amounts can kill people, you want to be, the sensitivity issue becomes the key driver. So this is what has led us to doing a variety of these on-chip things. Now, here's a chip, just as in our notional drawing of it that we put together, where in this case, the red represents chalcogenide glass waveguides. We looked at making an on-chip source, so we need a light source on the chip, and we did some work with our MIT partners to look at quantum dot doped chalcogenides for emission in the key spectral regions. We worked with our colleagues at MIT to develop on-chip compatible lead telluride detector materials. And again, they had to function in the spectral range of use, but they had to be assembled in a sequence that made them compatible with the chalcogenide processing on the chip. The blue discs represent resonators, which can amplify detection of certain species, and the green layer on top were nanofoams that were developed by Igor Luzanov and his team and my colleagues at Clemson. And what was special about these foams is that they chemically reacted such that they could deflate or not deflate in their foam structure upon exposure to various chemical species. So we had to think from the very beginning, and this is going to be a recurring theme in the rest of my talk, is we have to think about what are the other materials besides the glass that have to coexist on this chip, because you have to think about how do I make it then? So what's the sequence of order to deposit and pattern waveguides, sources, resonators, detectors, and foams onto a platform to allow the optical functionality to be maintained, but also the key goal of the chip sensing structure to be universally applied in a cost-effective way. So that gives you some illustrations. And if you look at some of our work in the mid-2000s on these centers, you can learn more about how we did this. So this just summarizes what I just said. On a multi-component chip, so this is an end view of one of those chips. So the underlying surface is silicon. It has a cladding layer. We typically bury our waveguide made out of chalcogenide glass underneath one of these resonators. Those were the blue discs on the prior structure. They typically have some kind of a coating. It could be a film or it could be a foam, which responds to the unknown thing that we are trying to detect. And you have to encapsulate it then essentially within a channel, because there's either a liquid or a gas that flows over in this on-chip structure to do the sensing. So what I've shown here, and it's meant just to be an understanding of all these different things that have to live on the same chip, here are your material options that are available to you for some of these various constituents in our on-chip structure. Here's what they need to be able to do and here are the materials that might fill the requirement. The challenge is, I think, as soon as you see this, is that there are a lot of different flavors of materials that are available to be used, but they're very different, and therefore it makes the manufacturing much more compact. So many possible options, but a lot of challenges to make them. So that's the challenge that we have when we're starting our process of engineering these materials for these applications. We very much have to think completely through the value chain, from the very fundamental material to the final package, and understand the environment that it has to live in to understand what I should choose for my materials of choice. So here's the key takeaway. The chalcogenide glasses that we're trying to engineer typically do not live alone. And so we can't make just one flavor of glass for our application. We have to have it vary in terms of chemistry to give us a variety, in this case, of refractive index and dispersion. That's the change in index over wavelength. We have to think, depending on the application, of how we make it, whether it's a bulk material, a planar material that has to be compatible with silicon, or a fiber, which has to be compatible with the way that we make the fiber and correspondingly clad it. So when people come to us and they say, Kathleen, we need a material that does this, 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 and this, I say, that's great. You need to prioritize this because, and as I'll talk about in a moment, there's the must-haves for your applications, and then there's the nice-to-haves. And everybody wants everything, but the reality is no one material can give you everything. So you really have to prioritize those, because there will be mismatch. And this mismatch affects how you design, because in most cases, if we're making optical materials or optical glasses, mismatch gives rise to loss, either absorption loss or scatter loss. It dramatically can impact fabrication. And it can affect longer-term in-service performance, because depending on whether the material is at static temperature, cycling temperature, ambient lab conditions, or flying in space, you need to understand that far-out application to understand how we can prioritize the properties that we want our material to have. Okay? The key takeaway here is the fact that we know what the knobs are. We can tune our material for those applications to hit the must-haves and do our best to give our customer the nice-to-haves. So let me come back to the reality now. We now have been able to make photonic integrated circuits where these materials are connected to the outside world through electronics. But we can essentially now realize all of these things that we envisioned back in 2011 now on a commercially available photonic chip. And the key thing that allowed this to be realized is our awareness of not only who the materials need to be, but most importantly, our ability to manufacture these multiple materials in a low-cost way. And so our work has fed directly into a lot of this integration work, which has been led by my collaborator, Professor J.J. Hugh at MIT. J.J. and his team really have thought about how the community makes electronic chips, so semiconductor chips, and now can translate those fabs or fabrication locations into being compatible to make photonics chips. There's always going to be an interface between electrons and photons, but you need to think about how to make it low cost, and that means modifying that. So JJ, you'll see if you look at our publications, JJ and our team have published a lot together since he was a graduate student starting at MIT back in 2004. And now he's a faculty member there, and his group is really one of the leading groups in photonic integration. Well, I'm excited to say that one of the spin-off companies that came out of MIT was specifically in this area of sensing for both either liquid or vapor phase chemical interaction, which takes this engineering of a structure similar to what was shown in our initial cartoon and has now shown that they can be engineered into compact packages for the application. So if you're interested, check out InSpec. So one more knob now, if we can make these materials in a cost-effective
Hi,
way.
my puppy. Hi, my puppy. Hi, my puppy.
Can we please mute the your microphones if you've joined us? Thank you so much. If we now know that we can make these films, we can now think about making these films with measurable good quality optical function. We can now think about making them for a variety of applications. And one of the real advantages that came out of some of our work on a flexible photonic solar project was showing how if you can put these films with their optical functions on low-cost substrates, such as polymers, you can now start to think about integrating and packaging them for a wide variety of lower cost applications, such as shown here. So challenges of material science, of course, at the end of the day, the component has to carry out its optical function. So that's the challenge. So I've given you a basic understanding of what the infrared system needs are. One of the most important things are, if the best designs that you might have, if you can't make it, it will never be realized. So you need to think about the ultimate end platform. I want to now talk a little bit more about how we tailor compositions, and when it comes down to it, are infrared glasses the solution for all problems? I think you know the answer. The answer is no. So how do we choose between crystals or glass to determine our material selection? This is not meant to be an eye chart. It was something that I put together for part of a publication we did several years ago that essentially identifies applications where chalcogenide glass or glass ceramics can be used. And it's meant to highlight not only what the applications could be, where these materials could be used, but the challenges, the critical properties, the fact that some are easier or more difficult to fabricate, and some are more easy or difficult to scale up. So the purpose here is not to be exhaustive, but it's meant to highlight as a takeaway some of the trade-offs involved with using infrared glasses and glass ceramics in a variety of applications. So that may be of interest to you. All right, so let's now talk a little bit more about the engineering side. So let's go into the infrared material design space. So here's a cartoon which illustrates refractive index as a function of dispersion, or Abbe number. Now, a low value of V, or Abbe number, is a high amount of dispersion. So going from, and what does that mean? Just as it says, dispersion means a wide variety of refractive index as a function of wavelength. So depending on what you want to design, you have in the infrared a finite source of options. You have semiconductors, you have what we typically call 2,6 crystals, you have fluorides and tellurides, and each of these are illustrated in the bubble graph next to the index and dispersion region typically covered by chalcogenide glasses. And this was a cartoon put together by one of my former students who was at Schott and now is at Edmund Optics, Nathan Carley. If you look at where the commercially available glasses sit in a similar glass chart, there are only 6 commercially available flavors of chalcogenide glasses, and they typically fall into this region of, this is partial dispersion versus Abbe number. But you can see, compared to many of the crystalline materials, zinc selenide, germanium, silicon, they typically occupy a fairly narrow spatial window. Compare that to the oxide glass chart, which most of you have probably at one point or another seen this oxide glass chart typically by Schott or any of the other glass manufacturers. The glasses that we're talking about are typically in this spatial region, so well aware from many of the oxide glasses. The other thing you'll notice is the 6 flavors of glass that are commercially available are extremely dwarfed by the many varieties of oxide glasses which you can make optics from. So we talk about what an infrared optical system needs to have? Well, I already showed you this complicated lens design, and this lens design is made up of 30 individual lenses, and they have very specific applications and target optical attributes that they must maintain. So this says that we need to, in many cases, engineer new materials that have optimized capabilities. And I'm not just going to say properties, but formability that would allow us to not only understand the optical function, which is easy if we think about just index and manufacturability into either spheres or aspheres or variety of shape, but we also need to know how these properties change with temperature, because in many applications, we have a variety of conditions. So what do we choose? A well-known optical design person in our field, Jay Viscavage, who's now running his own private company, did this as his undergraduate research project at the University of Arizona in the early 2000s. And this chart, taken from his research report, illustrates some of the trade-offs that optical designers need to think of. I've broken his chart up into areas where you can see where crystals, glasses, and some of the other materials that are typically considered as candidates for optical designs typically live, and some of the pros and cons of not only their properties, but their stability in a variety of thermomechanical and chemical environments. So no one material satisfies all the physical property needs necessary to support this reduced number of components in our optical design. So that means we have to make an optical design that typically has 2, 3, 4, sometimes 5 different of these materials, if we're talking about bulk systems, in them. So when I talked about those must-haves, the nice-to-haves, and where chalcogenides sometimes win this comparison, it's shown in the properties that we talk about here. Now, every optical system does not have all these variables needed, but these are typically the questions that a application design person has to answer if they want us to think about making a new material. So I talked about the physical properties, but the other thing is the scale. Is this customer looking to make 1 optical system, 100, 1,000,000 optical systems? And so that's where scalability and cost becomes extremely important. And from our perspective in the university research lab, if we're working with customers who want new materials, I very much need to understand these differentiator items, because I will make a one-off that's perfect, but if we need 1,000,000 of them, I might choose a totally different material system and manufacturing strategy. So the last thing I want to then finish up the last quarter of my talk on is just to take you through how we think about these things. So you saw this slide before, but I just want to highlight one of the key things. I mentioned that these glasses are typically made from group 6 constituents. You'll notice, however, that we eliminate oxygen because oxygen is an impurity. If there is oxygen in our glass, it will not transmit in the infrared. If there is oxygen in the form of OH, moisture, in the 2.93 micron spectral range, it will be an impurity and it will be an absorption loss ingredient. So we want to keep our materials oxygen free. So I mentioned that we want to be able to design our materials with knowledge of not only their refractive index over wavelength, that's what we call dispersion, but we also need to think about new materials that have to live in a variety of use environments. And one of the most important aspects is how these properties change with temperature. This is a figure taken from Bill Wolf's book and his paper in 1991 that shows a index, wavelength, and temperature isoplan for germanium, crystalline germanium, and how these materials change. This information is available for semiconductor materials, single element compounds, but largely does not exist for glasses. And this is important because if we want to design, we really need this information for our materials. So our group back in the late 2010 and 11 timeframe said, how do we go about engineering our material to understand the knobs of composition and how they can be used to predict thermo-optic properties, how these optical properties change with temperature, keeping in mind thermomechanical, the fact that if we change temperature, once we've made these materials, how do their mechanical and chemical properties, for example, change? Because these things dictate how we fabricate the component, how we have to coat it, because all of these materials have very high refractive indices. They have to have some kind of an AR coating, anti-reflective coating on them. And as I've hit back previously, they have to be compatible with other types of materials in our design. So I'm not going to go through this in a lot of detail, but suffice to say that my former student, Ben Gleason, did a great job on a very simple chalcogenide glass system, germanium arsenic selenide, where he showed that by relating through Raman spectroscopy, the constituencies between, in this particular case, the intensity of the germanium selenide Raman band could be used to, as a function of germanium content, engineer not only the glass transition temperature, the coefficient of thermal expansion, the mechanical properties, but also by understanding what the impact on these constituents were, depending on what the stoichiometry of the material was, either having excess chalcogen or group 6 element, in this case selenium, or a deficient amount, how the key aspects of, in this case, index and thermo-optic coefficient, or DNDT, changed as a function of these. Now, while he did this work for this simple germanium arsenic selenide system, what he showed is that, and we understand very nicely how to go from stoichiometry to either excess or deficient network structures. And so we can change who the ingredients are, but it gives us some insight in terms of designing these materials for these applications, thinking about not only their optical properties, but these properties which largely dictate the manufacturability. And Ben did a beautiful job of linking the chemistry, the structure, and the properties to allow us to now get into a mode where he showed we could, in a predictive way, engineer our materials to have a characteristic property. In this particular example, he was looking at having a glass that had a DNDT, or a change in index, close to 0 as a function of about 100°C temperature change. And he compared our predictive model with the large variety of published data that existed, and showed that we could use this historic understanding of these measured properties in our predictive model. So the point is that there are ways to engineer materials based on predictive methods, and we continue work in this area. So one of the last few things I want to talk about, and we've published a lot in the last 10 years on this, is in the area of gradient refractive index. Now, I mentioned in this, we can change the refractive index by changing the ingredients, the composition. And that's fine if we want to make a single element material, because the way we change how this lens works, for example, here's a typical cartoon of a lens where it's a homogeneous material. Refractive indices of chalcogenides are on the order of 2.4. The way we change focus is typically through changing the shape of this curvature of this lens. Gradient refractive index means instead of having a single index material, we have a material that can have a very flat, easily to manufacture form factor, but we change the gradation of the refractive index. So it's no longer one index. It goes from high to low or low to high. And if we can make a material that has a gradient, we make huge strides to make a lower swap or a smaller form factor component. So the key takeaway here is, can we make gradient index materials repeatably with arbitrary through 3D designed index variation that requires spatial control? So when I mean spatial control, I mean I don't only want to change the index radially in the lens from the center to the edge, but axially too, so that we can change the index going through the part. And I want to do this in a controlled way. So we've worked a lot on GRIN over the course of the last decade. I'm not going to go into a lot of details. We've done it in making glass ceramics. I'll talk about that a little bit more. We've been working with our colleagues at Bordeaux, where we have been able to use thermoelectric polling to change not only the composition and therefore the refractive index. If we can change the index in a spatially controlled way, we can change the shape of these lenslets so that we can make micro lens arrays, for example, both in the visible and the infrared. We've worked hard to develop process flexibility. So all of these vials contain different glasses in solution. And we were able to, either by 3D printing or electrospray, show that we can make gradients based on changing the thickness of the layers and their composition to make GRIN this way. And this allows us now to look at one of those cross sections on our chip with our resonators and change the local environment of refractive index that our sensor sees. And that means we can sense many different things by improving the contrast and therefore the resolution of detectability or sensitivity. And then lastly, we have done a lot of work on laser writing of metastructures, and I'll finish by talking about this. Here's an illustration of some of these gradient index glass ceramics, and we call these composites, where because we understand how we can use a laser source to nucleate and subsequently grow nanocrystalline materials in a homogeneous glass material. We start with a glass, we nucleate and grow these crystallites shown as green circles. We can change essentially the volume fraction and therefore the effective refractive index in this glass ceramic. So suffice to say, the more crystals, high index crystals you have in a low index glass, the higher the effective refractive index will be. So now I have a way, as long as my laser light can penetrate through my thick glass sample, to make a gradient by spatially controlling this in both axial and radial directions. There are very specific optical metrics that our glass ceramic must meet. And not only the optical properties, but the other physical properties will be a product or essentially an effective sum of the properties of the remaining glasses as well as the crystals that we have created. And they must be very small to make sure that we don't have scatter and loss in this composite. So we spent a lot of time working on this and have in both bulk and thin film form. It's shown here for a germanium arsenic lead selenide glass system, where lead is the key ingredient which promotes crystallization in a controlled way. But what you can see is that not only do we maintain transparency across the infrared in our base glass and our glass ceramic, but we have a huge change in refractive index that is available to us to engineer into an optical design platform. So what are the changes of these properties then when I create this secondary phase containing glass ceramic? Well, I show the key properties, and I lifted this cartoon or this table from the shot glass data sheet. Here are the properties shown in their data sheet for arsenic triselenide. And here are the properties of one of our base, we call GAPSI, germanium arsenic lead selenide base glasses, where the lead selenide content is 40 mole%. Here is the base glass, so no crystals. Here are the properties of the base glass. And here's what happens when I use a controlled nucleation and growth protocol. And the important thing to note is not only can we change the optical properties by a lot, but we can also change the dispersion. We can change the hardness. We don't change the density very much because the constituents that are there have only changed a little bit in terms of whether they're in the disordered amorphous state versus the crystalline state. And remember, in this particular example, we're talking about between 15 and 18 volume% of crystallites, and the crystallites are all sub-100 nanometers in size. So the volume fraction is nominal, but you can see now we have a knob to tune these properties. So this is important. So I hope I've convinced you up to this point that depending on whether we want bulk or planar optics for seeing or sensing, there's a number of things that we need to be able to do. And sometimes we can make them using traditional glass manufacturing processes, sometimes not. Here are those same solution-derived materials that we've made compatible with an electrospray process, where we can now spray or coat these materials on a variety of either silicon or flexible substrate materials. So again, having materials that not only exhibit their optical function, but are tunable is a real key attribute. So the last thing I'm going to talk about is some of the work we've done over the last 5 years as part of a DARPA-sponsored project on phase change materials. And for those of you that aren't as familiar with phase change materials, in our case, these are chalcogenides again, but they're alloys. And what's unique about these alloys is once they're deposited into thin film form, they start out amorphous, but upon a stimulus, whether it's thermal or electronic, we can convert them to a crystal and then retransform them back to their amorphous state. And typically, this is work from Professor Wuttig and Aachen, who wrote a wonderful review of these materials. They go through a change in types of bonding, which gives rise to a wide range of refractive index changes, as well as thereby reflectance and transmission. You're familiar with these because this is germanium antimony telluride is the historic legacy phase change material, which is commonly used in read-write DVDs. But for work in the mid-wave and long wave, these materials are too absorbing. They were engineered for fast switching times, which they need for that application, but unfortunately they have good switching, but high infrared loss. So we needed to engineer other materials. Well, working with the MIT team and our partners through our DARPA program, we made a compositional modification to the GST and showed that by reducing the amount of tellurium by substituting another chalcogen, selenium, we could make a GSST alloy, which has very low loss in the infrared and switches very nicely over a wide variety of applications. So here's an application now of this phase change behavior, and the movie that was showing here illustrates the active switching in this very central region where there was a heater, and the powers needed to do that switching. Here's a larger scale 1 centimeter by 1 centimeter illustration of what happens to the light when it couples into this structure, either in its amorphous state or its crystalline state. And depending on what the index is, of course, now that light sees a different indices and therefore focuses at a different spot. So this information allows us now to really engineer a structure that can go from 2 different focal positions, in this case, amorphous and crystalline, by actuation with a electrical switching pulse. Now, here's a static amorphous versus crystalline state. You can appreciate now if I can tune to someplace in between, we can now make a variable zoom structure. And that's exactly what we did as a result of this program. This, if you're interested in this, here is a demonstration of a imaging device. Shown here is the MIT campus. What was special about this is depending on whether we were in a micro or a macro focus scale, we showed that we could switch between a very narrow field of view to a very broad field of view. So you can appreciate if you have a camera that you want only one set of optics on. If I have a focusing or a switching element, which allows me to very quickly switch from tight focus to broad field of view focus, this is extremely important because it allows us to dramatically reduce swap. And this is the team associated with that DARPA program. So I'll just conclude by hoping I have done a good job of educating you a little bit on infrared glasses and the fact that if you can really understand this chemistry, structure, property relationship, but most importantly, how that translates into manufacturability, you have a whole portfolio of different things that you can do with these types of materials. You can make a wide variety of compositions with engineered properties. You can think about incorporating this optical or physical function onto a variety of platforms for device integration when these materials need to coexist with other materials. And our team's been extremely successful in being able to transfer exciting things out of our lab to commercial platforms. So that in one example, the grid materials we talked about, we've now transferred that material, and those materials may be available soon commercially towards to large-scale manufacturability. Hopefully, I've shown you that interdisciplinary is the key. And not only do you need really smart glass scientists, but you need to be able to work with and talk the language of optical designers, manufacturing and metrology people who understand how to make things and measure them, and to be able to design and manufacture things that exist in the robust environments associated with their future use. So with that, I'll thank you.